Right. Okay. So let's do from characters. Okay. So maybe having some problems. So this thing about characters, as I recall, it is going to be useful in order to prove the correspondence, in order to prove the or maybe the fundamental theorem of Galois theory. Okay. So let's see what it is. Yeah. So wait, someone has sent a message. But um, yeah, I don't know. Can others hear me? Yes. So then, yeah, you try. I mean, I'm recording it, but I don't know. Yeah. Okay. But you should be able to see me. Okay. So, so we are going to look at characters, or should be able to see the screen. Yeah. Right. So here now see characters, as I understand, have different definitions. There are different kinds of characters. Okay. But the one which we are looking at, maybe I can call it multiplicative character. Multiplicative. This is just a name I am giving. It uh, might not be useful or might not even be appropriate. But let's see. We will figure that out. Yeah, just sent him a message. Okay. So, so the definition G be a group. Okay. K. So I'm just copying the definition from the book. Okay. Yeah. Be a field, right? Then character is a group homomorphism I'll just use the same notation. Okay, so they don't have a notation. It's a group homomorphism tau from G to K star. Okay, so this is just the definition, and G is not necessarily a billion or anything. And when we say K star, we of course mean the multiplication of K, right? So we are talking about the multiplicative structure of K, and so K star is a group, right? Now, the key thing is about the independence of characters. Okay, that is really the key. That I think culminates to saying later that you cannot have. Uh, no, maybe I do not know. We'll have to see. Yep. Yeah, but the point is that the characters are independent. That is the main theorem. So theorem. Yeah, I'll just first write it like this. Characters are independent. And from this we can extrapolate, I suppose, but we should still write it. Before that, what someone is saying something. Okay. Before that, one question comes to mind at this question. Of course, first example, right? Yeah, sorry, very, very sorry. So, can anybody give an example of a character? Sorry. Anyone? I'm thinking, like I'm just thinking, so I don't know. No. So of course we know simple examples, right? We can just take identity. We can just take G equal to K star and then you take identity. That's a trivial example. And tau equal to identity. Any other example? So one example which is very fundamental in fact is, I mean, I'm not trying to give artificial example. Okay, I'm giving some, yeah, proper examples. So this, and you can take tau. Uh, yeah, so you can take tau to be, let me just write it and then I will say it to the power I alpha. What do I mean by this? I just mean multiplication by this. Okay. So yeah, the problem is that I should have said what do I mean by K. I did not say that. So K is C star. K is complex numbers. Okay. So what I am looking at is from S1 to C. I'm sorry, from S1 to C star. I'm looking at a group homomorphism, which is just taking this Z and multiplying it by this. Okay. So can anybody interpret this? What is this C star? Is it something? Is there something, some representation if you know? Hmm? So this is GL1C. That is C star. Yeah, if something, if I'm saying something wrong, just correct me. If there's something which is not clear, just ask. Okay. So otherwise, this is how it is. So you take S1, which is a circle, and you take C, and then you take GL1C, and then you take this group homomorphism. These are called one-dimensional representations. One-dimensional representations, right? So this is a representation because you're going from a group to GL something, and this is how the representation is. Okay. Oh, right. But okay. That will be okay. So let me check if is this a group homomorphism or not, right? That is the question first. And this answer is yes, this is a group homomorphism, right? Is that correct? So set one. Ha. This is what I am getting. Yeah, so is this a group homomorphism? Let's check that. If I take multiplication by this, Yes, yes, unfortunately, yes. What can I do? Uh, yes, we can talk about it. Yeah, okay. Yeah, so he's having some. I mean, he's in the car. He's not supposed to be in the car when he's having a class, but maybe, yeah. Anyways, okay, so that's let's now think about this. Yeah, but something is wrong about this example, maybe. So, because if I take z1, z2, that goes to e to the power I alpha z, right? Z1, z2. But yeah, but z1, yeah, so it's not a group homomorphism, right? So what is the correct way to say it? Yeah, right. So the correct way to say it is this. Thank you. That's why there was a confusion, I suppose. So it is just the alpha goes to this complex number. Yeah, right. Yeah. So yes. Yeah. So tau is just the exponential map or something like that. Or no, this is also wrong. Right. Yeah. Right. 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 Correct. That is the problem. So it's not correct. So what is the way then? Let's see. So we want to go from. So I just want an example of a character. Okay. So let's see. Yeah. So basically, I suppose it should just be the identity map, right? So you just take Z and you send it to Z. It is correct, of course, and it sounds a little underwhelming, but there's a meaning to it. Okay. So just take tau to be the identity map. Okay. So this cannot be wrong. Okay. Certainly correct. But if you just view it like this, okay, then you are sending it to the transformation, which is multiplication by z, which is the transformation which sends omega to z omega, right? So I'm taking z and I'm sending it to, it's now becoming a linear transformation there of C, an invertible linear transformation of C. In fact, it's a unitary transformation because it preserves its norm, because norm of z is 1. So we are down to again the unitary group U1C. So is it clear, Vaishnavi? Is it fine? This what this is doing? Yes. Which part? Which? Yes. So what we are trying to do is we are trying to take elements of the circle, right? And using that we are getting some linear transformation. So if I take an element of the circle, okay, now using that I want a linear transformation of C. So what do I take? I am just taking multiplication by that Z. Okay, that's becoming a linear transformation of C, isn't it? Number one, it's invertible. Number two, and also it preserves norm because norm of Z is one, right? So it is the same thing as identity map from Z S1 to C star, or inclusion map, you can say. But it is written in a maybe slightly fancy way. Okay, so that's it. There's nothing. Yeah. So this is an example of a character. Okay, and these characters are very important. So basically, uh, these are facts which maybe next time one of you can tell like give a formally present. If Arnav was there, but he's not here, so yeah, then it's so from that S. If you're taking this a map, a homomorphism from S1 to any UNC, okay, if you're taking any pi, this is also a character, yes or no? Because this is a group. I mean, okay, I'm sorry. It's probably no, because this is a group, but this is not the group of units of a field necessarily. So you don't really know if it's a character in this definition. But it's what is called a representation. It's a representation of S1. Then what you should maybe present is show that this S1, this pi is actually, well, in some sense, and if you just look up, you will realize is a direct sum of these. I mean, uh, yeah. So how do I say it? Right. So before going there, let me ask you to give me one more. Can anyone give me one more example of a of a character? I just need one more example. Try. S1 is a group, right? So give me one more example of character. Like we gave an example Z going to Z. Any other example? Just Z going to Z to the power n or any integer. These are all characters, right? Yeah. Please stop me if something is not clear. Sorry. Okay. So this is a these are characters, right? And basically the claim is that these are all characters. Okay. Characters from S1. These are the only characters. Z going to Z to the power n for some integer n. Okay. Now, this is number one, that these are all the characters. So what you should first try to prove is prove that if pi is a map meaning the group homomorphism from S1 to C star, then pi is equal to one of these. So this I will call phi n, or maybe tau n is better, right? Is equal to tau n for some n. This please prove this fact and present me. Okay, so this is number one. I mean, And both of you try it, and then one of you can present, and one of you can present the other, whichever you're comfortable with. Or maybe Vaishnavi, why don't you present this one? Because this is like purely group theory. This is you try to do this, okay? And so that's number one. And number two is which are what I was trying to say here. Yeah. So right, that if there is a group homomorphism C, okay, then show that pi is equal to uh, a direct sum of course it's going to be a finite direct sum uh, yeah of sorry pi I j's where j goes from 1 up to n. Okay, maybe Aditya, you can try to prove this. Okay, what I am trying to say is by this direct sum is that you can split this un into subspaces, one-dimensional subspaces, because every phi ij will correspond to a one-dimensional subspace, right? You can split Cn into one-dimensional subspace and write this homomorphism pi as a sum, means that each subspace will be invariant uh, under the image of S1 under pi. Okay, so it's a direct sum of representations. So this will break up into one-dimensional direct sum of one-dimensional representations. Okay, so you should try to prove this. First maybe the thing should be to formulate this precisely, because this is imprecise. Formulate this precisely and then prove this. But there is only one possible formulation, so you have to come up with it and then you present the proof. Okay. So this should be, yeah. And I suppose there are many things about these things, but I don't know anything about this much. This is all I know. uh, yes, I suppose the thing would be that it will never go, yeah, even if you're mapping it into GLNC, it will actually always map into UNC. Ah, okay. Under a basis change, it will also always map into UNC. See, I mean, UN depends on the basis, right? Whether a transformation is unitary or not depend on what is your orthogonal basis, right? Correct. And that depends on what is your inner product. My claim is that by changing the inner product, the image will always lie inside unitary. So basically the problem is reduced to this, but I'm not asking you to prove that part. You can do that, but then you have to do that thing that you can do a change of basis so that the image goes into UNC. Okay, you can do that if you like, but that's more work. You can try that. And this, but if you assume that it maps into UNC, then it is easier, I think, to yeah, find complements and so on. And this all this basically comes down to some facts that CS1 is a semi-simple whatever commutative algebra. But yeah, you can prove that also if you like. But essentially, you'll be proving this. And this is just the beginning. I mean, there are many things, the compact groups, and so there are some reasons why this is happening. But if you try that, then you will understand. Okay. And there are many things, but I'll not go into. There is a Fourier analysis here, and there is harmonic analysis here, and there are many things, but that will take us away from the topic. Our topic is to understand Galois theory, and of course, these representations in Galois theory come right because then then maybe we can start talking about Galois representations next time, or once we are done with this, see what happens. So let's come back to this result, which is elementary, but I suppose very useful. Yeah. Yes. So now I wrote that characters are independent. Now let us try to prove it. Okay. So what should the statement be? Statement should just be this. If you imagine, if you let your imagination, okay, then you will see that it will be this. If tau 1, tau 2, dot, tau n are characters, okay, uh, then sorry, equal to 0. And you know what this means as a function, right? From g to k star equal to 0 uh, implies, or as a function from g to k, implies that the ci's are 0 for all I. I mean, the proof is you can just read. It's nothing. That I'm not. We'll do the proof. That's fine. But one must understand what this statement is. Okay. First of all, you try to understand that these characters don't form a group under addition because there is simply no reason. Why we just saw that example z plus z square. This multiplication by this is not a character. Or maybe I'm sorry, I should say that uh, yeah, right. I mean z going to z plus z square, that's not a character from S1 to C star. Because I mean this will be 0, right? So it's not even in C star. Sum of characters is not a character, right? But when you take sum of characters and what happens, that is a fundamental question in mathematics. And here, if this purely formal, like even I think a computer can do this, just formally proving this is it's nothing. I mean, I suppose anyone can do this, but this is the first result, right? That what happens to sum of characters? The point of this theorem is what happens to sum of characters? Product of characters is a character. Is that correct? They form a group, right? Characters will form a group under multiplication. I mean, under multiplication, I mean, of course, under multiplication in K star. That's fine, right? Yes or no? That's, yeah. So that's a nice thing. The product of characters is a character, but sum of characters is not a character. And the question is, what happens to sum of characters? Here they are saying they are independent. Peter Weil theorem, or if you do functional analysis, they will say that if you take sum of characters, then they are dense in something. I mean, I can tell you what that is. They are dense in. Can I tell you what it is? Do I know? I don't know. I think yeah. Uh, if you have a Hilbert space, then they will say that they are dense in this. That's Peter Weil theorem. Okay, actually, the statement is slightly wrong. It's not characters are dense. It's a bit different. You have to take something called matrix coefficients of characters, but it comes down to this kind of thing only. Okay. So what happens to sum of characters is very important. And who finds the coefficients? Fourier. Fourier finds the coefficients of those characters. When you write something as sum of characters, then these coefficients come from Fourier. These are Fourier analysis. It comes from Fourier analysis. So this is a central question in mathematics, and I suppose there are many other things which I do not know, of course, about. So characters are very, 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 very important. Yeah, and of course, if you do like representation theory, you know that characters. Then there's a slightly different definition of characters. It's not multiplicative, but you can make it multiplicative by exponential or log. There you will see that characters determine the representation. But if you go to modular representation theory, like if you do representation theory where the base is not a whatever, where there is a problem where the base character defines divides the uh, size of the group, there the character doesn't define doesn't determine does not determine the representation, and that is good. It means that the representation brings out more of the group than just this whatever exercise we saw right now, that it can be written as sum of one dimensional representation. That's a bad thing. It's good news, but also it says that representation theory is not so useful. That's why we have to go to modular representation theory, because there characters are not enough. Okay? But otherwise, if you're in C, then characters are actually everything. If you want to study representation theory, character theory is everything. So I mean, this is just a beginning kind of a small thing which is purely formal. Okay. But anyway, see what it is. So characters are independent. We want to prove. We can just prove this anyhow, right? So you just assume this and try to prove that the Ci is as zero. Okay. So I mean, assume that's so let's prove it now quickly. But all these things are there to want to explore. So they're in front. So the proof maybe assume that this is zero, and assume that this uh, is minimal. What do I mean by this? Is better to say that this and no, wait. Yeah, sorry, huh? Right. You can go by induction. Yeah, so I'm basically doing induction only. You're right. So you want to go do induction on n, right? This n. Yes. Huh. Right. Correct. Yeah. So yes. So when you say when we say that we want to go by induction, we want to assume for, let's say that yeah, if it is true for n, like if combination of n of the things is equal to zero, then it is then each of them is zero, and using that you want to prove the next case, right? So that's like forward induction. What I am doing is the same thing. I'm kind of using the well ordering principle. Okay, I'm saying that assume that the theorem is false, and then take the smallest counter example, right? Assume that the theorem is false and take the smallest counter example. Look at the smallest n for which it is false, but then I will produce a smaller n for which it is false, and that will be a contradiction. And you see, that's the same thing as induction, right? Assume that it is true for 10 and prove it for 11, right? I will say that assume that I will say that, okay, if it is not true, then assume the smallest thing for which it is false, and then I'll produce a smaller thing for which it is false. That's like well ordering well ordering principle, not the well ordering theorem. That's different. That's axiom of choice. That's equivalent to axiom of choice. This is different, right? Vaishnavi, is this point clear that the well ordering principle thing and induction, they are the same things, and that's because the natural numbers are well ordered in a natural way. Okay, so yeah, so let's do by induction, because I mean, if that is the let's do direct induction. Okay, if that is a suggestion, then we should try to see where it takes us. Because I was doing well ordering because I just read it, okay, in the past. But let's see how induction will work, right? Something but as I said, logically they are equivalent. One may be more convenient though. Assume that maybe so as Eritrea said that the base case is trivial, so that's easy. Uh, yeah, let's write K here implies dot 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 dot. k is equal to 0 for all k. Okay. So yeah, this is assume. Now let yeah, I should be consistent in the way I write, which I'm not. That's not good. Now, how do we reduce? So we have to do a trick. We have to do some trick. That's all. So what does this mean? This means that this is true for all g, right? So this as a function, of course, the space of all functions from g to k, that is a vector space because k is a vector space, not k star, right? The set of all functions from g to k, that's a vector space. So we are using that. And in that context, this is 0. Or this is linearly independent in that vector space. So it kind of says that there cannot be too many characters. That's what it says. Cannot be too many characters because they are independent. And this is true for all g. So the trick is just you have a gh and so on, right? So this is no. So what do you do? Hmm. Yeah, you just do a gh. So take tau 1 h, tau 1 g. Yes. Okay. Tau 1 and tau k plus 1, right? Is that okay? Yeah. Yes. So you do that and so maybe that's the h which we have. Yeah, I think I've introduced means I've written it unnecessarily, so I have to repeat it. Yeah. So I will just say where tau 1 and tau 2 differ. I don't want to go to k plus 1, right? I mean, you can use the statement for any k taus. It doesn't have to be the same k taus, right? So, yeah. uh, yeah, anyways. So this is equal to 0. And now, as suggested, so you just take this equation and multiply both sides by tau 1h, right? And then you subtract. Yeah, correct. You subtract. And then you see that you get a smaller relation. You get a relation with k terms. Any k, we don't care, but it has some k terms, right? And so let's write that precisely. So you have the C2 tau 1h minus C2 tau 2h, right? uh, yeah, tau 2 plus, so this is like the coefficient, right? Plus tau 3 and so on. I mean, there will be some coefficients and things like that, equal to 0. And now by induction, what do we know? We know that all these things are 0. Like this is 0. Okay. But as we assume that tau 1 h is not equal to tau 2 h, that's what Aditya said, that you take tau 1 and tau k plus 1. But anyway, that's the same thing. So I'm taking this, and this is 0. So C is so so it means C2 is 0, right? This implies C2 is 0. And I mean, I suppose, yeah, in that way you get everything is 0. All the CIs are 0 and whatever. So it just finishes it. Is it fine? Is proof fine? Characters are random. I mean, I've not done the last few details, but I think we are convinced. Okay. Okay. Yes, and then this is used to prove that the Galois group cannot be larger, because every element of the Galois group is basically a character. Maybe that's the examples which we should have done rather than doing the examples of S1 that we did, right? And that was rather foolish of us. Correct, that should have done examples, because Gal KF, uh, that, I mean, there is a map from there to case to okay, yeah, but then it is to automorphisms of K star. Yeah, anyway, so it's not direct, but it's probably uh, yeah, probably something. Probably that's what is called a Galois representation. Right? It's maps into the. It's a representation of the Galois group. Okay, but anyways, we'll come to that next time. Maybe we'll just stop here today, and we will let Vaishnavi describe her experience about the camp. Maybe you can do that on a Jamboard if you have the if you are ready to write at the moment.